So welcome everyone to the last recording of topic number 2. In this recording, we will cover two parts of the flexure design or flexure capacity of cross sections. The first one will, after we finish the rectangular section, we will focus on what's so-called many time T sections, and also cases where you have negative reinforcement. So as we promised, the second topic will be covered in 4 recordings. In class, it actually was covered in 7 lectures. So the focus will be today for T-beams or non-rectangular beams and doubly reinforced beams. So first of all, a T-beam, if you have a concrete slab supported over beams, drop beams, in this case, you will result in a section that is actually called T-beam or T-girder. In this case, we will be asked to calculate what's so-called the effective width. The only big difference between rectangular section and T-section is the presence of two widths. The first one is B flange, and the second one is B web. However, in a rectangular section, you only have one width, which is B. So most of the time, B web will be provided. Total structural depth D will be provided, and also the thickness of the slab, HF. ACI table 632.1 provide guidance on the distances to calculate the effective flange width B. So the effective flange width B will be the least of, if you have a beam that is extended in each side of the web, each distance here, if you call it star, and a star, will be the least of 8 times HF, which is the depth of the slab. So this is going to be star. And S web divided by 2, which is S web is this distance. And L divided by 12. So you can see here, effective overhang flange width beyond the face of the web. So to calculate that, you will have to get B equal the least of 3 values. The first one will be 16 HF, because we have 8 from the side and 8 from the side plus BW. Or SW plus B web, or L over Ln over L is the span of the beam. L over 8 each side will give you L over 4 if you multiply by 2. And in this case, we will not add BW because it's a function of the length of the girder, not the cross sections. But if you have it extended from one side, so it's more like an L section, some textbook called L section, you will have 3 values. The first one will be B web plus 6 HF or SW over 2 plus B web or L divided by 6. Actually, L divided by 12. So in this case, we will have in the T-beams two cases, because since we have B web and B flange, we will have two possibilities. The first possibility that when you do the capacity analysis, that the neutral axis for stresses will be within the flange, or it will be actually within the web. So to determine the minimum, first of all, what we need to do is to keep the basic equation, C equal T, and moment equal C or T times R. The first quantity we will do is we're gonna use CT equal T. However, in this case, we will use, instead of before 0.85 F prime C A times B, we will replace A times B by area concrete required, AC. So in this case, if you are provided by AS and F yield, you can get T, because T equal AS times F yield. You have F prime C, you can calculate what's also called AC. From this case, the AC will be tension T, which is AS F yield divided by 0.5 F prime C. From this case, we will compare AC to area of the flange, AC flange, which is basically HF times PF. If AC is less than or equal area concrete flange, you are in case one, which is neutral axis for stresses is within the flange. If area required is more than area flange, so you need to recall the web to engage, this is going to be case two, where is neutral axis for stresses in the web. Let's get through one example. Example number one, determine the design strength Φmn of a T-beam in the following figure. In this figure, we have P effective width PF equals 60 inches. The B web equal 10 inches. D equal 24 inches. HF 4 inches, and AS is 6 inch square. Concrete is F prime C is 4,000 psi. Steel grade 60, so I feel the 60,000 psi. The beam has a span of 30 feet. Cast integrally with 4-inch slab. Clear spacing between the girders 50 inches. In this example, it was meant not to provide effective width, but I've asked you to check it. So if you check the equation that we have before, you have 16 HF plus BW, 16 times 4 plus 10 is 74 inches. The second one will be B web plus SW which is 50 here, is W, will give you B should be around 60. And last one is the span divided by 4. In this case, it's 90, and the least of all will be 60 inches, which what we calculated or provided here. So B effective is 60 inches. So let's calculate AF minimum. AF minimum, you will have two equations. The first one is 3 square root of prime C divided by Fy BWD 3 square root of 4,000 psi divided by 60,000 psi times 10 Pweb D is 24. It give you 0.76 inch square. And also you have to check 200 BWD of Fy, which is 200 times 10 times 24 divided by 60.8. 6 inch square is more than 0.8 inch square. So you are okay to proceed with the section. Let's calculate AS. AS is 6 provided as 6 inch square. F yield is 60. So in this case, if you use 60 KSI and use 6 inch square, you got force of 360 kips from the tensile. Let's calculate area concrete required. Is a tension divided by 0.85 F prime C. 360 kips divided by 0.85 if divided by 4, it gives you 105.88 inches square. However, area of the flange is 4 times 60, 240. Your area AC is less than area of flange, so the neutral axis has to be within the flange. You can calculate A as AC divided by B flange, because the neutral axis now is within the flange, or you can use the same equation that we have before. In this case, AS F yield divided by 0.85 F prime C, F prime C, and in this case, it's going to be B flange. If you take notes, this is a value AC. So if you divide AC by 60, give you 1.676, which is pretty much the A value. You know, concrete is beta 1 is 4,000. F prime C is 4,000 psi, so beta 1 is 0.85 in this case. So if you give C equal A divided by beta 1, 1.76 divided by 0.85 is 2.07. If you got strain steel, epsilon T is D minus C divided by C times 0.03. D in this case, we know that is D is 24. C is calculated as 2.07. C D multiplied by 0.03 will give you a strain of 0.0318, which is way more than 0.05. So your phi value is 0.9. Section is ductile. In order to calculate the moment, Phi you have to calculate arm. In this case, arm will be D minus A over 2. So it's 24 minus 1.76 divided by 2, give you 23.12. Phi is 0.9, as we know. Tension times arm. Tension, you know, 360. Arm is 23.12. The moment is 7,490.9 kip inch. Divide by 12 will give you 624.2 kip foot. And this was the case number 1, where you have the neutral axis within the flange. We will have another example where we will deal with neutral axis in the web. In this case, effective width is 30 inches. HF, BF, so-called BF. HF is 4 inches. D is 30 inches. 14 inches B web. And AS is number 10 will give you 10.12 inch square. F prime C is 4,000. If yield is 60,000 psi or 60 ksi, was grade 60. Same tracks that we did before for S minimum. I will not spend time, but the value here is 1.4, and we will provide 10.12, so we are okay. Let's calculate T in this case. T is S by F yield. It gives you 10.12 times 60, so 607.2 or 607.2 kips. To calculate area concrete required, extension divided by 0.85 F prime C. T is T divided by 0.85 prime C. T is 607 or 607.2 or 607.2 divided by 0.85 if which F prime C is 4 ksi. Give you area required of 178.59 inch square. However, if you calculate 30 by 4, which is the area of the flange only, it will be 120. So in this case, area required is more than the area flange, so the neutral axis in the web. You need to add the web to make the balance. In this case, you can take the difference between area required and area of the web, and this will be 58.6. If you divide this 58.6 by 14, it's gonna give you 14.19, which is this coordinate here. We can call it F. So F equal 4.19, and therefore A is equal H flange plus F, which is 8.19. You can also calculate the neutral axis of those area from the top, for example. The area of the flange is 120. You can multiply by 2. Distance from centroid of this flange to the top is 4 divided by 2. And the other area is 5.58.6 inch squared. And the R at the distance between the neutral axis, this distance is 4 plus 4.19 over 2. If you divide all by the area, 178.6, you get the neutral axis of this shape is around 3.34 inches from the top. Now we can calculate actually A, as we mentioned before, it's HF plus F value, assuming this is the F value here. It's 8.19. You know, beta 1 is 0.85 because F prime C is 4 ksi. So C will be 9.65. Epsilon T, strain in tensile reinforcement, D minus C divided by C times 0.03. This will give you 30, which is a depth here, minus C, which is 9.64, divided by C, 9.64, times 0.03. It gives you 0.00634 more than 0.05. Section is ductile, and phi is 0.9. Now we need to calculate for this area, for this example, the moment, and the moment will be similar to what we calculated before, except of in this case, you will have C1 and C2, C1 plus C2. C1 is going to be 0.85 prime C, HF, BF, and C2 is 0.85 F prime C times B web times F. The arm of this one is actually the arm will be d minus hf over 2. However, for the second force, the arm will be d minus hf minus f over 2. And it can take the summation of, for moment, mn can be summation of c times arm. In this case will be c1 times arm 1, c2 times arm 2. There's another method here, which I pretty much didn't cover in the class, so you can give it a read. The first one will be, it's pretty much try to convert the cross section to be a rectangular section, which is easy to solve, and part of the flanges. So area of the flanges here can be calculated, and you can equalize that to part of the steel. You can calculate area steel equivalent to the overhang of flanges, and area of steel equivalent to the web. And you can take the moment from the both and adding them up, but I didn't cover it in the class, and you are free to read it. And solve the example and check and come and ask during the office hours for more information. And one thing you need to make sure that you may have a T section, but you solve it as rectangular section if you have, for example, this cross section, but you have a negative moment. So if you have a negative moment, the moment looks like that. Tensile will be in the top side. Compression will be in the bottom side. So you're always going to have a rectangular section. So this is the end of the T sections. We will start now doing the compression steel. Compression steel, in some cases, you will have to use it in cases where with normal actually proportionals, compression steel is normally not required. If the section size is restricted, compression steel may be used. If compression steel is used, additional tensile steel must be added if flexure capacity is to be increased. Adding compression steel only has little effect on flexure design strength. So in this case, you can consider a cross section with compression steel AS dash. We're gonna call it AS dash. Tensile steel is AS. As contribution of two moments. The first one is a concrete section, the entire rectangular section, an AS1, and a section that doesn't have any concrete, but only reinforcement. The first one will be AS dash, and the other one will be AS2. In this case, the moment nominal one will be AS1 if yield times D minus A over 2, because the distance is D, and A value here as we have before. So it's really similar to rectangular section. However, Mn2 will be AS dash Fs dash D minus D dash. You need to know that D dash is the distance now from the top or the compression fiber to the compression steel centroid, and Fs dash is stresses in the compression steel. We need to know if it's yielded or not, unlike the tensile has to be yielded. So let's get started. The first part that you're going to calculate is A. In this case, A will be equal AS1 if yield divided by 0.85 if prime CB, assuming that you have to get AS1. Mn1 will be S1 field D minus A over 2. Second part is going to be AS dash Fs dash D minus D dash. In this case, you don't know if steel is yielded or not. So let's go through an assignment to know if steel is yielded or not. Before we go to the example, this is going to be the strain distribution and forces or stress distribution. In this case, steel will be epsilon T. In the concrete will be a crushing strain 0.03. You have C value, as we have before, we have linear line. However, we have a coordinate here is epsilon S dash. In this case, epsilon S dash can be by interpolation calculated as epsilon S dash divided by D minus C minus D dash equal 0.03 divided by C. If you rearrange the equation, epsilon S dash would be equal C minus D divided by C times 0.03. In order to get actually A value, you have to use the first equation, C equal T. In this case, you will have two C's, C, which is C of concrete, and another one, CS dash. C of concrete is regular, as we know before, 0.85 F prime C AB. CS dash are going to be AS dash FS dash. Okay. We don't know if it's yielded or not. And intention is always AS F yield. So the first equation, we're going to assume the steel in compression AS dash is yielded. In doing so, C equal T equation will be T is AS F yield. C is 0.85 F prime C. Instead of A, you can also represent A by beta 1C and B as the width. And AS dash plus AS dash F yield, which is CS dash, assuming FS dash is yielded, steel is yielded. Now you can solve the equation for C. And also you can get A as beta 1C. Small. You can get epsilon S dash, which is C minus D divided by C times 1/3. If your epsilon S dash actually is more than epsilon yield, which is F yield divided by modulus of elasticity of reinforcing steel epsilon S, which is always 29,000 psi, mean that your assumption was correct that steel in compression is yielded. So in this case, if it's not yielded, you cannot use assumption that Fs dash is equal to F yield. It's not valid anymore. So we can take the equation that we just developed for epsilon S dash as C minus D dash divided by C times 0.03 and multiply time ES modulus of elasticity, it give you Fs dash. So in this equation, the equilibrium will be Fs, F yield equal 0.85 F prime C beta 1 CB, and the other part, which is Fs dash, is here as we prove it, C minus D dash divided by C times 0.03 times ES times AS dash. You can now solve this equation for C, and as you solve it for C, you can calculate epsilon S dash again and see if it's yielded or not. So let's solve few problems, couple of problems actually. The first one, where steel we know gonna be not yielded. In this example, we have a BW, width of the cross section 14, overall depth 27. Two covers. The bottom cover is 3 inches, leading D to be 27 minus 3 or 24 inches. D dash is 2.5. AS is for number 11, which is 6.25. And AS dash is given as 2 inches, 2 inch square, which is to number 9. The first step is assuming steel is compression is yielded. Write the equation C equal T. This is T. Yes, if yield. C in this case will be CC, C in compression, plus CS dash. CC is 0.85 F prime C A B, or you can call it beta 1C B, because beta 1C is equal A. This is equal A, you know that. Plus F prime C F yield. So Fs is 6.25 inch square. F yield is 60.85 equal 0.85. In this case, concrete was F prime C was 3, B is 14, beta 1 is 0.85, and C is unknown, and AS dash is 12 inches square. F yield, Fs dash is equal, F yield is equal to 60. So can you solve for this one? C is 8.4 inches. You can calculate A as equal beta 1C, 7.14. Let's check our assumption for Fs dash. Epsilon S dash equals C minus D dash divided by C times 0.03. You know C is calculated as 8.4. Those are the C's. And D dash is given as 1.5 times 0.03. It gives you 0.002011, which is thankfully more than the yielding of the steel, which is 0.0207. So compression steel is yielded. Now you have the values for C1, C2. You know C1, CC is 0.85. 5 F prime C, AB. You have all the values here. You can calculate it. And its arm is RM1 is D minus A over 2. D is 24 and A is given 7.14. Calculated actually. You know now a CS dash is if yield, because it's yielded, time AS dash. So in this case, it's going to be 2 times 60. It's going to be 120. And the arm is of distance between the compression steel to tension steel. In this case, going to be D minus arm 2 is D minus D dash equal 21.5. Now we can take summation of C times arm to get Mn, which is going to be CC times arm 1 plus C2 CS dash times arm 2. There is another method that you can calculate. You can calculate what's so-called AS2, and in this case, AS2 is Fs dash divided by F yield. In this case, AS2 will be equal to 2, and AS1 is going to be AS minus AS dash, or AS2, going to be 6.25 minus 2, and going to be 4.25. This is another way of solving it. You can calculate. You have to calculate if steel yielded in tension from the famous equation epsilon T D minus C of divided by C times 0.03 give you strain if 0.05 0.0557 more than 0.05 phi equal 0.9. Very good news. And now you can calculate from this equation directly, as we have AS1 calculated and AS2 or AS dash, or as we mentioned a couple of slides ago, by calculating the forces on arms separately. For compression steel not yielded, we have a different cross section. Total depth is 27, so structural depth in this case will be 24. Very similar as before, which is 14. The only change is now we drop this compression steel to 1.2 inch square. So this is S dash, and AS is 5.006. F prime C is 4,000 psi. F yield is 60. First, we have to assume steel is yielded, same as before. A S field tension here is going to be the force. Tension would be the AS times a field. CC will be 0.85 F prime C B beta 1 C. You have 0.85. F prime C is 4. B is 14. 0.85 is beta 1. C is not given. We have to calculate it. Assuming F is compression steel yielded, so F S dash is equal to field 60 times A S dash 1.2. I give you C as 5.72. Calculating A as beta 1 C. Beta 1 is 0.85 because F prime C is 4. Give you A as 4.86. Let's calculate and double check if steel is yielded given that C is 5.72. Epsilon S dash equals C minus D dash divided by C times 0.03. In this case, 5.72 minus 2.5 divided by 5.72 times 0.03 give you 0.0017 almost, which is less than the yielding. So compression steel is not yielding. Now you have to recalculate again because your first equation that you use is not valid. You have to resolve the equation using AS dash times FS dash, which is here, AS times FS dash. In this case, AS fields remain the same as 5.06 times 60. Concrete equation side is 0.85 F prime C B beta 1 C remain the same. However, we replace now F yield by Fs dash, which is C minus D dash divided by C times 0.03 ES. And in this equation, we solve for C. If you try to solve this equation, C is 6 inches, beta 1 is 5.1. Now you can calculate the forces as before, CC dash, CS dash on the arms, arm 1 and arm 2. In this case, CC dash 0.85 F prime C A B, and the arm is equal, arm 1 is D minus A over 2, and CS dash in this case is Fs dash, which you can calculate it, and As dash, and arm 2 is D minus D dash, or the second method, if you calculate here, you can calculate As1 and As dash as we did before, and the answer will be 488.6 kip foot. Thank you for tuning in. This is the end of this topic number 2. I'm looking forward to connecting with you on the next recording for topic number 3, which is a shear.